Hello and welcome back to your Chem 4 lecture. We are carrying on in Chapter 7. So we've talked about the mole in Chapter 7, and we've talked about how to balance chemical reactions. Now, in this lecture, we're going to talk about how we classify chemical reactions. And I'm going to tell you there's about, let's see, we can count them down here. We got 1, 2, 3, 4, 5 different types of reactions that you're going to be able to want to recognize. And then we'll have a sixth one, oxidation reduction reactions, on top of that by the next section. So this is just a way of classifying chemical reactions where we can then kind of understand, oh, this follows this pattern. So we call it this chemical reaction. And hopefully that'll make more sense as we look into it. So starting from the simplest type of chemical reaction, I'll list the names here first. We're going from combination to decomposition to single replacement to double replacement, and then finally combustion reactions. So those are the 5 types we're going to classify through the lecture today. So a combination reaction is exactly what it sounds like. It's where you take 2 or more products and they form, you take 2 or more reactants and form a single product. So you can have smaller compounds combined to form one bigger compound, or you can have 2 elements combined to form one element, like for example, or one compound, excuse me. So if you take 2 moles of magnesium reacting with 1 mole of oxygen gas to produce 2 moles of magnesium oxide, this is a combination reaction where the magnesium and oxygen combine to form the product, magnesium oxide. The generic form is listed here. I think this is a useful way to look at it. Think of it like A plus B forms AB. That also happens down here for molecules. So if you take sulfur trioxide gas and you bubble it through water, you form sulfuric acid, H2SO4. So again, that's a combination reaction because you have 1, 2 reactants and just a single product. Here's another example of a combination reaction. We're going to do some of these in lab on Monday. And I think this is one of the ones that we're doing. You take a magnesium strip and burn it in air. And when you do that, you form magnesium oxide. That's magnesium plus oxygen from air forming magnesium oxide. A decomposition reaction is just the opposite of a combination reaction. That's where a single reactant splits into multiple products. So the generic form is AB reacts to form A plus B. For example, this happens with mercury oxide, mercury 2 oxide, to form liquid mercury and gaseous oxygen. So this is decomposing from a compound into the constituent elements. KClO3 is another example of this. If you heat potassium chlorate, you produce potassium chloride and oxygen. So the compound splits into 2 different substances. And this is another example. Of course, this isn't one that we would do in lab because it involves mercury. But if you take mercury 2 oxide and heat it, you end up with liquid mercury and then gaseous oxygen. Okay, so those are the relatively straightforward ones. The next 2 are a little bit more difficult to describe. We have single replacement and then double replacement reactions. So in a single replacement reaction, one element takes the place of a different element in another compound. So basically, you always have an element plus a compound, and then you have a switch. The generic form is you take an element A and react it with a compound BC. You end up with a product AC, and then the element B is left over. The way I always think about this is it's like at a dance where one person cuts in to a dance, and they form a new dancing pair. So A is cutting in to B and C who are dancing, and that forms a new dancing pair, A and C, and then B is left, on its own for B. That's how I think of it anyway. Some examples here would be zinc reacting with hydrochloric acid to produce zinc chloride and hydrogen gas. Note here, the compound HCl, that's hydrogen combined with chlorine. Well, zinc takes the place of hydrogen here, and now it's partnered with chlorine to form zinc chloride and H2 gas. So hydrogen's left out as its own element form. The same thing here, iron reacts with copper 2 sulfate to produce iron 2 sulfate and copper. Again, iron just takes the place of a copper in the compound. I hope that makes sense. Okay, and here's another example. This is one of the reactions that we'll be doing in lab. You take a zinc strip and you put it in hydrochloric acid, and you start to see bubbles form. Well, what's happening there is the zinc is replacing the hydrogen in hydrogen chloride, and so it's forming a zinc chloride solution, and that leaves hydrogen all alone as its element form, which is a gas, H2 gas. Okay, so that brings us to double replacement, which is even a little more complicated. This basically is going to be a reaction between two ionic compounds where the positive ions swap places. So if you want to continue the dancing analogy, this is like a do-si-do, where you have two partners dancing, and then the do-si-do happens, they've switched partners. So if we're going to do it in a generic form here, it's AB reacting with CD to produce AD and CB. So note here, the cations stay as the cations. A is a cation in the reactant side, and it's a cation in the product side as well. It's just that it's combined with anion from the other one. So it's the cation of the first picks up the anion of the second, and the cation of the second picks up the anion of the first. So again, they just swap places. So an example would be like this: silver nitrate acting with sodium chloride. That produces silver chloride and sodium nitrate. Or zinc sulfide reacting with hydrochloric acid produces zinc chloride and H2S. Okay, and we'll definitely have some of these in lab as well. I think there's one or two that we're going to do in lab. So here's sodium sulfate reacting with barium chloride. That produces barium sulfate, which is a solid compound. That solid compound, once it forms, undergoes what we call precipitation. So it crashes out of the reaction, is how we say it, where these over here were dissolved in water. Now all of a sudden they're no longer dissolved. So we see kind of a dramatic production of this solid as it precipitates out. Okay, so that's the double replacement reaction. Finally, we have the combustion reaction. The combustion reaction is exactly what it sounds like. It's where you take a compound that contains carbon and you burn it in oxygen gas. So you're burning something that contains carbon, and the products are always carbon dioxide and water and some amount of energy. So for example, methane and propane here, two components of natural gas. Methane, CH4, reacts with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. You can recognize it because your reactant is a carbon-containing compound and oxygen. And then your products are always carbon dioxide and water. Okay, so those are the 5 types of reactions. And we'll have a sample exercise down below. But before we're done, we want to talk about incomplete combustion because this is very relevant to health professionals, because anytime that there's a combustion reaction that's going on in an enclosed space, that can be a very dangerous, I should say enclosed air space, that can be a very dangerous situation. Of course, this is why a fireplace has a chimney, right? That's so that the smoke can exit the room. But if you don't have adequate ventilation, some of the products of combustion are not always going to be carbon dioxide and water. Some of it, if it doesn't burn all the way, will produce carbon monoxide, or CO. Here's an example of that reaction. And the way you can think about it is, it's just sometimes the fire isn't hot enough, or the molecule isn't exposed to the right oxygen. There's not enough oxygen in one part of the burning wood, let's say. And that just leads to, an inability to form carbon dioxide, which is energetically preferred, and produces carbon monoxide instead. Now, the problem is carbon monoxide is itself a colorless, odorless, and poisonous gas. And when you inhale it, it attaches almost irreversibly to hemoglobin molecules. So hemoglobin, you've probably heard of before. That's the oxygen carrying system in our blood. And it does a dual role, right? In when hemoglobin gets close to the lungs, it picks up oxygen from the lungs, and then it's pumped by our blood throughout our whole bodies, to everywhere that needs it, from our brain to our toes. Not only that, though, once it delivers the oxygen, hemoglobin also then picks up carbon dioxide where it is. So carbon dioxide weakly binds to the hemoglobin and then brings it back to the lungs, where the carbon dioxide is released, and the oxygen then binds to the hemoglobin and then goes back around. So it's a really kind of a beautiful system where the same molecule will pick up the oxygen and deliver it. And then once it's where the oxygen needs to go, it'll pick up the carbon dioxide and get rid of that. Now, there's a big problem here, which is that carbon monoxide interferes with this system in a real way, which is that carbon monoxide is a stronger binder of hemoglobin than is oxygen. So oxygen binds hemoglobin a little bit more strongly than CO2. And that's important because once it gets to the lungs, you want to make sure that the oxygen is there to displace the CO2. And that's great that it works out that way. But carbon monoxide is very, very strongly attracted to the iron in hemoglobin, where again, oxygen or carbon dioxide would be. So carbon monoxide gets on the hemoglobin, and then all of a sudden, it's stuck there. It's not going to come off no matter where it is, in your lungs, in your extremities, wherever it happens to be. And that's going to lead to, of course, a lack of oxygen in the bloodstream. So as soon as you have this exposure to carbon monoxide, you'll have a reduction in your ability to exercise. Yeah, of course. Your visual perception will go away, and your manual dexterity also, because again, in your extremities, that's where you're going to first notice the lack of oxygen, and in your brain, of course. When this hemoglobin bound to carbon monoxide reaches about 10%, that's when you're going to have shortness of breath, a mild headache, and drowsiness. If it gets to 30%, that's when dizziness, mental confusion, severe headache, and nausea will hit. And then finally, at 50%, a person could become unconscious and die if not immediately given oxygen treatments. So yeah, so that's carbon monoxide. That's the dangers of carbon monoxide breathing. Interestingly, cyanide works in a very similar way, although it's a little bit more poisonous. And it's not a gas. Okay, so there's our reaction types, right? So we've got combination, decomposition, single replacement, double replacement, and combustion as our 5 types of reactions. And we're about to add oxidation reduction, but hold on to that. Okay, so we're finally ready for sample exercise number 9. For A through D, tell me, classify each of these as either combination, decomposition, combustion, single replacement, or double replacement. So go ahead, pause the video, look these over. You can always go back to here and use this as kind of a guide to help you understand it for now. But go ahead, pause the video. And when you come back, we will take a look at the answer. So go ahead, pause. Okay, I'm going to assume you're back now. So sample exercise number 9. First up, we have A. Now, A has an element, aluminum, reacting with a compound, sulfuric acid. And then what happens is you form aluminum sulfate and hydrogen gas. So which one does this look like? Well, it looks to me like aluminum is cutting into the hydrogen sulfate or sulfuric acid and forming aluminum sulfate, and that's replacing hydrogen, and that's being formed as an element. So that would be a single replacement reaction because you just have aluminum cutting in, forming a new compound, and producing, leaving the other one as an element. Okay, next up we have sodium sulfate plus silver nitrate, 2 silver nitrate, reacts to form silver sulfate and 2 sodium nitrate. Well, what do we have here? This is where we have our do-si-do, right? This is the double replacement reaction where sodium is the cation of the first, is going to pick up the anion of the second, nitrate, to form sodium nitrate. The cation of the second, silver, picks up the anion of the first, sulfate, to form silver sulfate. So double replacement reaction. Next up, we have 3 moles of carbon reacting with 1 mole of iron 3 oxide to produce 2 moles of iron and 3 moles of carbon monoxide. Well, it looks like we start with an element in a compound, and then this element picks up the partner of this compound, right, the oxygen, and that leaves the first part of this compound as an element. So this seems to be like a single replacement reaction to me. Then finally, C2H4 plus 3 oxygens yields 2 CO2 and 2 H2O. This is a clear case of a combustion reaction. We have a carbon-containing product and oxygen producing carbon dioxide and water. Okay, so we got single, double, combination. Wait, I see. Okay, hold on. Okay, so this is definitely a single displacement, right? But this one here is a combination here where nitrogen reacts with oxygen to form 2 nitrogen monoxide. Okay, let's do it again. Let's have some more fun here. Identify each as combination, decomposition, combustion, single replacement, double replacement. Pause the video, work out sample exercise number 10, and when you're back, or when you're done, we'll be back. Okay, so I'm assuming that you've done it here. So let's go ahead and just go through it real quick. A, we have barium plus nitrogen forming barium nitride. That is clearly a combination reaction. A plus B forms AB. Next up, we have silver plus hydrosulfuric acid produces silver sulfide and hydrogen gas. This is yet another indication or another example of a single replacement reaction. Silver is going to form a compound with sulfur, leaving hydrogen on its own. 2C2H6 plus 7O2 yields 4 CO2 and 6 H2O. Well, that is a combustion reaction because we have carbon-containing reactant plus oxygen yielding CO2 and H2O as products. Next up, lead 2 chloride plus potassium sulfate forms potassium chloride and lead 2 sulfate. This is a double replacement reaction where we have the cation of the first picking up the anion of the second, the cation of the second picking up the anion of the first. Okay, then K2CO3, that's potassium carbonate forming potassium oxide and CO2. This is clearly a decomposition reaction where the first compound, the reactant is just a single reactant and forms 2 products. So yeah, combination, single combustion, double decomposition. Great. Okay, so now we are going to look at oxidation reduction reactions here in section 7.6. One big example here is rust. When rust forms, that's an example of an oxidation reduction reaction. Oxidation and reduction just focuses on the transfer of electrons. And so we want to understand them so that we can kind of understand how they're useful both in technology and in our bodies. Okay, so an oxidation reduction reaction occurs when we metabolize food. Also occurs when batteries give up electricity. And finally, it occurs when iron rusts and in many other types of chemical reactions. What happens is, in an oxidation reduction reaction, electrons gets transferred from one reactant to the other. So if we say A reacts with B to form our new products, if A gives up an electron to B, A is oxidized, is what we say. A becomes oxidized because it loses an electron. And then B becomes reduced because it gains an electron. Now, there's a couple ways that you can remember this. One mnemonic is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So if something gains electrons, it's reduced. If it loses electrons, it's oxidized. The other one is Leo goes Ger. Loss of electrons is oxidation. Gain of electrons is reduction. So Leo and Ger. Whatever mnemonic you like to use is totally fine. Rusting is an example of this, and there's an analogous process for copper. So the Statue of Liberty is made out of copper, right? But it doesn't look like copper, right? Copper we know is like an orange metal. Well, that's because when copper is exposed to air, it undergoes a rusting process where it forms copper 2 oxide. In this, when you have solid copper forming a copper 2 ion, it has to give up electrons. So the copper gets oxidized to the copper-2 ion, and it gives up those electrons to oxygen. Oxygen, when it gains electrons, it forms the oxide ion. So clearly it is reduced. The other way that you can make sure that you understand the reduction part is when something gains electrons, its charge gets lower, right? It gets more negative. So that's the original kind of starting point for this word reduction. Okay, now there's a lot of cool ways that you can, there's a lot of cool things you can do with this. If you take a solution of aqueous copper-2 ions and you stick a strip of zinc in there, zinc will actually reduce copper. And you could also look at it this way, the copper-2 ion will oxidize zinc, where the copper-2 ion will pick up 2 electrons and form copper metal, which is what we're familiar with. And then the zinc metal will give up those 2 electrons and form a zinc ion. So basically you're replacing zinc atoms with copper atoms. And so this is one way that you can get copper plating on a surface. Okay, so given that, remember, oxidation is loss of electrons, reduction is gain of electrons. Identify the following reactions as either oxidation or reduction. We've got tin metal going to tin 4 ion and producing 4 electrons. We have the iron 3 ion reacting with 1 electron and forming iron 2 ion. And then finally, we have chlorine reacting with 2 electrons to form 2 chloride ions. So see if my explanation worked here. If not, we're going to walk through each of these to make sure that we understand it. There's a really easy shorthand that will help you with this, but I want to see if you get it first. So let's go ahead, pause the video, and work out oxidation versus reduction for A through C. Okay, I'm going to assume that you're back now. Well, the really easy shorthand is that if you have an electron as a product, that means that whatever you're looking at was oxidized. In other words, this tin lost 4 electrons, so tin got oxidized. Likewise, if an electron is the reactant, then you have a reduction. This iron 3 ion gained 1 electron, so it became the iron 2 ion. So it gained electrons, so it was reduced. So oxidation, reduction, and reduction for our answers here. Okay. All right, now this is fun. In a light-sensitive UV sunglasses, UV light initiates an oxidation reduction reaction where 2 silver ions react with 2 chloride ions to form 2 silver atoms and 1 chlorine atom. So given all of this, can you tell me which reactant was oxidized and which reaction was reduced? So think through what we said, and then we'll walk it through when we come back. So go ahead, pause the video here, try to think it out. Which was oxidized, which was reduced? Your options are the silver ion or the chloride ion. So go ahead, pause the video, and we'll come back. Okay, so when you have this type of problem, what you want to focus is on the charge, okay? The silver ion has a +1 charge. And then in the products, it has a 0 charge. How is that possible? Well, the only way to go from a +1 charge to a 0 charge is if you gain an electron. What does that mean? If you gain an electron, you are reduced. Same thing here with chlorine. The chloride ion has a -1 charge, and as chlorine, it has a 0 charge. So how are you going to lose that -1 charge? Well, it's if you lose an electron. Loss of electron is oxidation. So therefore, chlorine was oxidized, or chloride ion was oxidized, I should say, and the silver ion was reduced. Okay, now those are all kind of interesting for various reasons, but the main reason we introduce oxidation and reduction now is because we're going to need to understand it when we talk about biological systems. So you may have heard of some of these in your biology classes, coenzymes like FAD or NAD+. We have oxidation and reduction constantly occurring in biological systems as a way to take energy from food and turn it into energy that we can use in our cells. So here's an example. The coenzyme FAD, which is the flavin adenine dinucleotide, can be reduced to FADH2 by the transfer of 2 hydrogen atoms with the 2 electrons that go there. So it's 2 protons plus 2 electrons. And these 2 hydrogens can come from a variety of sources. And as an example, we're going to start with talking about oxidation reduction of methanol. This is actually pretty poisonous, so it's not like it's not, you know, the main thing that your body does, but it is just like a useful, simple molecule for us to be able to understand. So starting from methyl alcohol can be oxidized to formaldehyde by ripping off basically 2 hydrogen atoms. These hydrogen atoms are then transferred to a coenzyme, just like FAD. This formaldehyde molecule is then oxidized to formic acid by the addition of oxygen. Then this formic acid can be combined with oxygen to produce 2 carbon dioxide molecules and 2 water molecules. The problem is formic acid and formaldehyde are toxic, and they can mess up your cells. So that's where you actually have this toxicity coming from ethanol. But this is just an example. We'll talk more in depth about this once we get to chapters 16, 17, and 18. Okay, so right, so the whether or not you can identify an oxidation reaction is kind of important. So we want to give you some general ways of looking at them. So remember that oxidation is always going to involve a loss of electrons. And sometimes it's easier to track it by tracking the addition of oxygen. So anytime you react a molecule with oxygen, there's generally some oxidation involved, hence the name oxidation. The other way that you can look at it in a biological system is if something loses hydrogen atoms, that's the equivalent of being oxidized. So if FADH2 becomes FAD, well, it lost 2 hydrogen atoms. So that's another indication of oxidation. Reduction is the opposite. Always it is going to involve gain of electrons, but sometimes it's easier to see it when you look at, did this compound lose oxygen? If it lost oxygen, that means it was likely reduced. Likewise, if it gained hydrogen atoms, both the proton and the electron, then you can also look at that as a reduction. Again, that's the example of FAD being reduced to FADH2. Okay, so that takes us through this lecture. We're going to talk a lot more about oxidation reduction later in this class, but we just want to be familiar with the word before we get to the really complicated stuff in the biochemistry section. So that does it for today, but we have one last lecture for this chapter. And after that, we will be all done with chapter 7. So until then, I will see you later. And let me know in the comments if you have any questions. Bye-bye.